sorry. Okay. Can you hear me now? Yeah. Okay, so what we want to do is to generalize the infinite line bundle of line current to a general case of a source current. And here we assume that the source current is localized here, as in this object, and we want to find out what's the divergence and the curl of the B field generated by this source current here. And now this is actually similar to this multiple expansion in the sense that here this prime R prime vectors are for the source, and here this R vector is for this observation point, and then we also have this separation vector curly R, and so the B field is the integration over all this source. Sorry, I think I had a typo that didn't change. So this is curly R, this is curly R squared. So here the B field is a integration or superposition of all this volume current. And now let's be very careful about the R and R prime, because we want to find out the divergence and the curl of the B field, B of R, right? And this R vector is x, y, and z. So when we take the divergence and the curl of B, what we do is the del operator is always applying to this R vector instead of this R prime vector. So this is something that we need to pay attention to. So just as we say that if we take a del to this B, then it's some reasonable function. But if we take a del to this J, then this, because the J is a function of R prime, so the del dot J should be equal to 0, because J is a constant to R. And this separation vector both is dependent on R and R prime, and the volume element is on over this R prime. Now we can try to calculate the divergence first. So the del dot B can be simply evaluated by putting this del inside of this integral. Sorry. I may have put the wrong version. So all this should be curly R. So here we simply move this del inside of this integral, and because of this, we can use a product rule to evaluate this del dot J cross curly R hat. So this is we can if you still you can look this up from the first page or the last page of the Griffiths book, but you can also derive this by yourself easily. So you can imagine that the A dot B cross C can be rewritten as B dot C cross A, and C dot A cross B. And now because we want to apply this del operator to both the J and the function over here, so we have to rearrange this C cross A to be minus A cross C. So here we can rewrite this as minus A cross C. and now we can simply replace the a by a del vector, and here there are two terms because the del needs to be applied to both terms. And so if we write in these two terms, then we it's equivalent to a chain rule where the partial fg equals partial f times g plus partial g times f. So now here there are two terms, and the first term, just as we said, that because the j is a function of r prime, so the del cross j must be 0. And the second term is actually something that we just calculated in the homework 0. So you can also imagine that this is actually the electric field of point charge, and this one is actually 0 if r curly r is not 0. So the del dot b, this entire term should be 0 because both two expressions are 0. Now let's take a look at the curl of b. So the curl of b, we can do the similar thing, but just replace this del dot operator by this del cross operator. And here the cross product is still the similar thing. So we can use the back cab rule. So the A cross B cross C, if I remember correctly, should be A dot C minus C A dot B. But you can always refer to this front page of the Griffiths to double check the expression. And here, because there is a del operator, the del operator, the expression for this back cab rule needs to be modified, because here this del needs to be applied to both j and the function here. So in principle, there are 4 terms, and but we neglected some of them because just we calculate the del operator operating on the j is 0. So only 2 terms left, and these 2 terms are the del operator operating on this function of curly r. And now again we have 2 terms here, and the second term is something a bit complicated, but for now we actually claim that this term should be go to 0. And what's left over here is the first term, and the first term is if we evaluate the expression of the first term, it's actually related to this function. Is also something that we calculate in the E-field chapter. The del dot 1 over r curly r hat over r square is the divergence of the electric field, and that gives 4 pi times del cubed. And now keep combining these terms and the 0. What we arrive here finally is del curl b should be equals to this j times delta function, where this delta function is the of the separation vector, where the separation vector is r minus r prime. And now this integral simply means that we need to change the r prime vector to this r, and then this simply goes back to the expression that we derived earlier of del cross B equals to mu naught J. Then what we have left is to prove that the second term here equals to 0. And so to prove that, we can simply, the first step to prove this expression is 0 is to rewrite this del in terms of del prime. So because on the right hand side it's a function of the separation vector, and here the separation vector is simply r minus r prime, and partial x of a function of x minus x prime equal to the minus partial x prime of x minus x prime. So using this spirit, this can be we can also replace this del operator by minus del prime. So why do we need to change this del to del prime? So the reason that we prefer a del prime is because in the end we need to do an integral that's over the prime vector, and this del prime combined with the volume integral, if we arrange this properly, we might reduce the volume integral into a surface integral. So here, this is a three-dimensional vector quantity. So let's find out the one of the components first, and the other will be similar. Say that we find out what's the x component. So for the x component, because we write this as x minus x prime, so on the bottom it should be a separation vector cubed instead of square. And now evaluating this expression again, we can use the integration by parts or the chain rule. So we can first express this del prime on both two sides, and minus the function, but apply this del prime into the other vector. So this is in principle similar to this f partial g equals to partial f g minus g partial f. And now let's take a look at the second term. So the second term here, for a magnetostatic case, remember that we have the continuity equation, that the divergence of a current equals to the I'm not sure if it's negative or positive. So it's this expression, so it's a negative partial rho partial t. So here it's negative partial rho of partial t. So this is the continuity equation. And because For steady state systems, there's no charge change as a function of time, so it's 0. So here, this term is equal to 0. And so what's left over is only a del prime operator applying on this bracket on the right. And now the second term is the integral that involves this divergence operator. And according to the divergence theorem, this integral can be rewritten as a surface integral. And because we are looking at a finite size source, and at infinity, this j must go to 0. And so on the right hand side, this eventually goes to 0 because we can consider infinitely large integration. So here, this integration, remember that it's the integration over the source. So even though we are discussing integration over the entire space, we are still looking of the source that's over the R prime vector. So we are still looking at the B field at a single point of R. So this means that we actually prove del cross B equals to mu times J at everywhere. So what you need to remember is simply the Ampere's law. So we just derived this differential form, and so this del cross B equals mu naught J. And now this is a differential form, but we can apply the Stokes theorem on the left-hand side and change the surface integral to a line integral of the b dot dl, and then this b dot dl is equal to the mu naught times integration of the j over surface, and the j over a surface is simply the current enclosed. So in the integration form of the Ampere's law is simply the integration of the b times dl equals to this mu naught times the current enclosed. So this is the same as what we derive for this infinitely long bundle of wires. And now we actually see there's if we compare the electrostatic case and the magnetostatic case, we both have the we have the source, and the source generates the E field by the Coulomb's law, and the source current generates the B field by the Biot-Savart law, and the divergence of the E field is related to this Gauss law, and the curl of B is related to the Ampere's law. So we derive the Gauss law from the Coulomb's law, and the same here, we derive the Ampere's law from the Biot-Savart law. And these two are two observations, and these two are the from the Maxwell's equations. Do you have any questions? Okay. No more questions? Okay. So you can also post online, like if you want. Okay. So let's try to look at some of the applications of the Ampere's law. So the Ampere's law in the integration form is similar to applying the Gauss law in the sense that only for certain problems with very high symmetries it's beneficial to apply the Ampere's law. So for example, we have some application here that has high symmetry. So first, we can look at the case of infinitely long wire. We just calculate the B field for this case, right? So we already know the answer. The B field should be mu naught I over 2 pi s along the phi direction. But from the Ampere's law, this result can actually be easily obtained. So first, before we apply the Ampere's law, what we need to do is to determine the direction of the magnetic field. So this is a bit tricky because we first need to get an intuition where the magnetic field direction should be. So for this, the first case, it's a bit easy because we know about the right-hand rule. So for a current going to the right is the magnetic field direction is simply follow the direction of the four fingers over here. So it must be along the phi direction. And now if we calculate the so the Gaussian surface here changed to Ampere's loop, and so here along this Ampere's loop we have the, is that the correct pronunciation? Amperian. I don't know how to pronounce this, but it's similar to the Gaussian. So it's an analogy of Gaussian surface. So here in this, let's call this Amperian. Okay. Amperian. Okay, Amperian. Okay. Let's say this Amperian. And in this loop, the B field is a constant. So the BDL is simply B times 2 pi s. And then the the current enclosed is equal to mu naught I. So now we immediately get that the B is mu naught I over 2 pi s. So you have to be careful about the direction of the B field. Here the B field is to the phi direction. So you can, in principle, get that from the right-hand rule, or from this from this integral alone as well, because here the integration here is the surface of the integration is directional, and so you have to be careful about the sign of this I enclosed. Typically, you can imagine that if we integrate from 0 to 2 pi across a loop like this, then the I should be pointing out of this paper. And you can always sort of verify this direction by using the right-hand rule of your infinitely long wire to where this direction is the current direction and the forefinger is the direction of the magnetic field. So say for another example is the on the right hand side, we consider surface currents on this xy plane, and now we are interested in the magnetic field generated by this surface current. So we must define a direction of this surface current because it's a vector. So in this case, we define the k to be along the x direction. And now we need to first determine the direction of this magnetic field. So if we consider the surface current as a superposition of many line currents, then you can sort of imagine that for a surface current pointing along the x direction, the magnetic field will be something like this. And now for us, however, there won't be any z component because of the cancellation of all these sources. So in the end, the surface current will be only along the y direction. So so in the end here, we are only interested into finding out the B field along the y direction, and now we can design Amperian loop, where there is a there is a loop where it's a rectangle that's going upwards, slightly upwards to the surface, and also across the below of the surface. And because of the symmetry, the B field on top should be on the of the opposite direction on below. So the BDL must be equals to B times twice of this length, and then what's enclosed is simply the K times L. Sorry, there should be also additional mu naught. So what we have here is that By must be equals to KL mu naught over 2L, which is mu naught over 2 times K. However, we need to make sure that the B is along this minus y direction for this plus for the upper plane, and it's on the y direction on the lower plane. So here, before you apply the Ampere's law, you have to be careful that you need to figure out what's the direction of your magnetic field. So otherwise, because in principle you have to determine the B field along x and y z direction. So for example, let's take another look at the final example. So here we are trying to calculate the we want to calculate the magnetic field of a solenoid. So for a solenoid, you can think of as many loops of wires that form the cylinder. but this loop of wires are so tight that they looks like as if the surface current, and so in principle there is a current that's going upwards, but the current going upwards is much less than the current going along the circumferential direction. So for simplicity, we can simply replace that by a surface current K, where this K equals N times I, where this N is the number of wraps around the solenoid per unit length. So for this problem, again, what we need to figure out is what is the direction of this magnetic field. So first, there should be no radial direction of this B field. So the B crossing this radial direction should be 0, because say that there are some radial direction magnetic field, and then if you flip the sign of the current, in principle the B radial should also flip, right? But here in this case, flipping the sign of the current is simply moving the solenoid from upside down, so that doesn't change anything. So here this BR should be exactly 0, and then what we are not sure is about is there any angular direction or a circumferential B field, and so to get that, we can to get the B along the circumferential direction, or the azimuthal, or you can say this as the phi direction. We can design Amperian loop as the one over here, because this the B times the B phi times the 2 pi L equals to the I enclosed. However, remember that here we already ignore the current flowing up, so this B circumferential, or the B along the this I enclosed is negligible, or we consider this as 0 for the case on the right. So there are no B field along this phi direction either. So the only possible B field is along this Z direction. So now, to calculate the B field along the Z direction, we can design an Amperian loop first across the outside. So if we design any Amperian loop at the outside, then this B at a radius A times L, sorry, minus B times B, this is the B dl across the loop, and because there are no currents on the surface here, so this integral is 0, which means that the BA must equals to B at a radius B. However, we know that at a place that's infinitely far away from this solenoid, the B field must decay to 0. So this means that B outside has to be 0. Otherwise, it will give a finite contribution at infinity. And now, because the B outside is 0, so we can make use of this by designing an Amperian loop that goes across the solenoid. So this is the Amperian loop number 2. So then we can have this B inside times the length equals to this mu naught times I enclosed. So the I enclosed must equal to this n times I times L. So the n times I is the k, and the L is the unit length. So k times L equals to I. So here we then have the B inside equals to mu naught I, and we can also figure out the direction of this B field. So say that it's going say this K is going the right hand side, then the magnetic field should be pointing upwards according to the right hand rule. So the B vector should be mu naught, sorry, there's n, mu naught ni, where the direction is z hat. So that's inside, and it's also 0 outside. So here, this solenoid is really special in the magnetostatic case. You see that outside of this solenoid, the magnetic field is strictly 0. And inside the solenoid, the magnetic field is actually a constant everywhere. So this is really a parallel example comparing to a capacitor in electrostatic problem. So the capacitor has a constant E field inside the capacitor and 0 outside. And where here for the solenoid, it's the constant inside and 0 outside. So it's really concentrate all this magnetic field inside a small cavity. Okay, so this finished the lecture today. So next time we will discuss the vector potentials and summarize the magnetostatics in vacuum. So this will finish chapter 5, and you can already start your homework. There are only about 2 questions that you cannot do about the vector potential and about the magnetic multiple expansion. So for all the other questions, you can already finish now.